Okay, so this video is designed to try and help you understand a quite complicated topic within the Earth Life Support Systems module. So this is all about cloud formation, and it covers ideas to do with dew point and adiabatic lapse rate and other types of lapse rates and things that people generally find quite confusing and hard because they are quite challenging. So a few things we need to cover to start off with, because they're important for understanding this, is um, first of all that we have these terms ELR, or environmental lapse rate, DALR, dry adiabatic lapse rate, and SALR, which is saturated adiabatic lapse rate, and we need to understand what these mean. So the the environmental lapse rate is the amount the atmosphere cools as you go up through it. So if we look at this diagram here, we've got ELR and we've got 6.5 degrees per kilometre. And if you look at the temperatures on the side here, we start at 13 degrees, and if we go up a kilometre, so 1,000 metres, we are at 6.5, because 13 minus the 6.5 ELR is 6.5. And then if we go up another kilometre, it takes us to 0. So we've lost another 6.5. So that's the idea there, is that if you were to just rise up through the atmosphere, this is the rate at which temperature would cool. Okay. Dry adiabatic lapse rate is the rate at which a pocket of air cools as it rises up through the atmosphere when it is not yet 100% humidity. So it's got some moisture within it, but that moisture is remaining as a gas, as a vapor, and is not condensing. Okay, we then finally have SALR, saturated adiabatic lapse rate, and this is the degree of cooling that happens per kilometre once the air parcel reaches 100% humidity, also known as the dew point, and the water vapour begins to condense. Now, the first thing we need to understand to make some sense of this is that condensation is exothermic as a reaction. Okay, so evaporation, which is the opposite of condensation, takes in heat. You have to put a pan on the hob, on the heat, for the water to evaporate, so the opposite of evaporation, condensation, will logically therefore be exothermic. It will give out heat. The heat that is given out is called latent heat. So this means hidden heat. It's heat hidden within the water vapour, and it's released as the moisture begins to condense. What this means is that saturated air cools down at a slower rate than dry air. And the reason for this is that the energy that's being released through the condensation. Okay, so if you look at this diagram, dry air is cooling at 10 degrees per kilometre, whereas saturated air is cooling at 7 degrees per kilometre, and it's saturated once it hits the dew point. So in this situation, we can see that the dew point here is 8 degrees. So once the parcel of air that's rising, the pocket of air, hits 8 degrees, it is then a saturated parcel of air. If you were to use a probe to test the humidity in that parcel, it would be at 100% humidity, and it is actively condensing liquid, which is why we get a cloud, and therefore it is now cooling at a slower rate. Okay, so we can see this in action here. So as with that before, we've got the ELR here on the right hand side, the environmental lapse rate, reducing at 6.5 degrees for every kilometre. And we have a parcel of air down here, which is currently at 18 degrees, and that parcel of air has been heated by the sun through radiation. So, what's actually happened is the sun has heated the ground surface by radiation. And then the ground has gotten warm, and that has conducted heat to the air above it. And so that air now will begin to convect and rise. These are all terms from sort of GCSE science, and if you've sort of forgotten what they mean, it's probably worth just looking them up again. So that all makes sense. So the air parcel is going to rise because it has expanded due to being heated up and is therefore less dense and more buoyant than the air around it. Okay, so the heat causes the air parcel to expand relative to the air that's not being heated around it. This makes it less dense, more buoyant, and therefore it rises. Once the air in the parcel becomes equal in terms of expansion with the air around it, it will stop rising. So if we have a look, we're at 18 degrees. The surrounding so we're at 18, the surrounding air is 13, therefore, because the air parcel is warmer, it is more buoyant than the air around it, and it will rise. After the first kilometre, the air parcel has lost 10 degrees. It's lost 10 degrees because it is currently dry air, because it's not at 100% humidity, so it's losing 10 degrees every kilometre. So we've gone from 18 degrees to 8 degrees. Now, 8 degrees, as you can see here, is the dew point. Therefore, at this point, the air is now at 100% humidity, and every kilometre it rises beyond this point, it is going to do so at the saturated adiabatic lapse rate because the air is now saturated. Now, again, if we have a look at the kilometre point here, the environmental lapse rate is 6.5 and the air parcel is 8 degrees. Therefore, the air parcel is warmer and so therefore less dense and more buoyant and will continue to rise. Though at this point it's now rising at the saturated adiabatic lapse rate. This is 7 degrees, so at the next kilometre it is now 1 degree and the surrounding air is 0 degrees. So it's still warmer, it's still more buoyant, and it's still going to keep rising. Another kilometre goes by and it's now -6, it's lost another 7 degrees, and it is compared to the -6.5, which is the surrounding air. So it's still warmer by half a degree, and it's still more buoyant. When it hits the final kilometre, so it's another 7 degrees, it's now at -13. The surrounding air is at -13, therefore the cloud stops rising, or the pocket of air stops rising, and this is the top of the cloud. It can't go any further because it is now in equilibrium with the air around it. Okay. The one final thing to come back to is this term adiabatic. What this means is, as the pocket of air rises, the air it moves up through is going to get less and less dense. This is because air molecules are held close to the planet's surface by gravity, and so as you rise through the air gets thinner. This is why people who climb Everest have to take oxygen tanks with them, because the air is a lot thinner, and therefore it's harder to breathe. So as the air rises, the amount of it causes the parcel of air to expand. Okay, you can imagine this if you can find videos on YouTube that show that if you put a balloon in a vacuum, the balloon will expand because the air within the balloon is of a higher pressure relative to the air around it, because you've removed air particles from around it. Okay, and the same happens as the parcel of air rises through the atmosphere. As it rises, the amount of molecules around it decreases, and so it becomes relatively higher pressure. And we can see this in the diagram, that the parcel of air, the same amount of molecules are getting larger as they rise, and the bubble is getting larger. Now, because it is being forced to expand without having heat introduced, what this does is cause the air to cool down. It's a bit of a confusing concept, but basically, if you apply heat to something, that causes it to expand. If you force something to expand without applying heat, it causes it to lose heat, basically. So this is why the parcel of air cools as it rises. Essentially, it's due to the expansion. Now, if the reverse happens, if the air sinks in a high pressure system, then the air will heat up and it will become warmer and more compressed. Okay, you can see examples of this as well. So, like if you use a gas canister for camping, then as you use it, the air is leaving the canister and it's getting less compressed, and the canister will start to get condensation on it because it's getting cold. So, because it's losing air and it's getting less dense air inside. Okay, so we can apply this learning to this worksheet here. So just notice that in this situation, ELR is 5 degrees, DALR is 10 degrees, and SALR is 7.5 degrees, and the dew point is 10. Okay, so slightly different to the explanation that we've just had, but it makes it a little bit easier to manage in this example. Okay, so if we come down to here, we can see that we've got a range of examples in which the temperature at the surface and of the air parcel that's starting off is at different temperatures. Okay, so the first one is at 15 degrees. Sorry, the ELR starts off at 15 degrees and the first parcel starts off at 30 degrees. Because the ELR is 5 degrees per kilometre, by the first kilometre it has dropped to 10, the second kilometre it's dropped to 5, 0, and so on. So it's dropping at 5 degrees each time. What we need to do is figure out where this cloud is going to form and where's it going to stop. It's starting at 30 degrees and it's dropping at 10 degrees every kilometre at the dry adiabatic lapse rate until the cloud starts to form. So when we get to the first kilometre, the parcel of air that we've got is now going to be 20 degrees because it's lost 10. At the next kilometre, the parcel of air is now going to be at 10 degrees because it's lost a further 10, and if we remember, the dew point is 10 degrees, so this is where the cloud will form, and this is why I've drawn the base in to help you on this first one. We're now dropping at 7.5 degrees for every kilometre. Okay, so we're going to start our cloud off. At this point, we are at 7.5 degrees and the surrounding air is at 0. So we're good. We're going to keep rising because the air in the cloud is more buoyant than the air around it. We've now lost another 7.5. So the cloud is at 0 and the air around it is at 5. So we're going to keep rising up. And at this point, we are now at minus 7.5. And the air around us is at minus 10. So we're still warmer, we're still more buoyant. So we're going to keep rising. And at this point, the surrounding air is at minus 15, minus 7.5, minus a further 7.5 puts us on minus 15. So at this point, our cloud has finished. It is complete because it is now equal in density with the surrounding air. Okay, so there's a few more examples here to have a go at. Some of them get a bit more challenging because they start with not on a whole number or not on a round number, so that makes it a bit more challenging, but you can have a go at seeing if you can apply it to the others on the worksheet.